In this video, we'll be learning how to solve logarithmic equations. These are equations, as the one you can see here, where the x appears inside of a logarithm. And then, as always, we have to find a specific value for x such that this equality sign holds true. As always, the timestamps for each exercise can be found in the comment section down below, where you can also ask any questions you might have along the way. You can also join our community and visit the Discord server, of which the link can be found in the description below. We'll be covering the 3 different scenarios that you might come across when solving logarithmic equations. We'll be solving several equations for each scenario. We'll start with the easy ones and we'll end off with the more complex ones. And the first equation that we're going to tackle is the following one. We have the logarithm with base 2 of x plus 3, which has to be equal to the logarithm, again with base 2, of the number 4. And this is the easiest kind of logarithmic equation that you can come across, because the only terms in this equation is the left-hand side, which is a logarithm of base 2, and the right-hand side, which is also a logarithm of base 2. And because each term in this equation is a logarithm with the same base, we can simply take what is inside of the logarithm and drop the logarithms altogether. Therefore, in this case, we find that x plus 3 on the left-hand side has to be equal to 4. And this can of course be very easily rearranged to get that x has to be equal to 1. And this is already our first solution. And this solution can in fact be very easily checked by plugging it in our original equation. If we have x is equal to 1, then we have the logarithm with base 2 of 4 on the left-hand side, which is of course equal to the logarithm base 2 of the number 4. And that's how easily such equations where we have a logarithm of the same base in each of the terms can be solved. The second exercise will be the following one. We have the logarithm of 2 times x, which is equal to the logarithm of x minus 5. And in this case, you might notice that I didn't write a base number for these logarithms. Well, this is simply the case because by convention, the logarithm without a base number is assumed to be the logarithm with a base 10. Because it is so often used in other applications, we can simply drop the 10 and we are left with the logarithm without a base, but we know that it is base 10. And we immediately see that we can solve this equation in the same way as we did before, because the only terms that appear in this equation are logarithms with the same base, namely the base 10. And this allows us to only consider what is inside of the logarithms. This gives us the following equation. We have 2x on the left-hand side has to be equal to x minus 5. Now this can of course also be very easily rearranged. So we have 2x minus x is equal to minus 5. Or written differently, we have that x is equal to minus 5. And we already have our solution, which again can be very easily checked if we plug it in our original equation. Since 2 times minus 5 is minus 10, and if we put in minus 5 here, we have minus 5, which is also minus 10. So this solution is definitely correct. So these types of logarithmic equations are quite straightforward to solve. So let's now go to another scenario where we are not able to simply drop the logarithms. And the first exercise is the logarithm of base 3 of 5x minus 2, which has to be equal to 2. Now we clearly see here that on the left-hand side we do have a logarithmic term, but on the right-hand side, we don't have a logarithmic term. So we cannot just drop the logarithm and work with what's inside. In these cases, there is another procedure that we can use, namely to exponentiate both sides of the equality sign with as a base number the base of the logarithm. And why this is, we'll see in a minute. So we get 3 to the power of the logarithm of base 3 of 5x minus 2 on the left-hand side, and 3 to the power of 2 on the right-hand side. So what we did here is just exponentiate both sides of the equality sign with a 3 as a base number. And at this point, we can use the property of the logarithm, or even the definition of the logarithm. Because if we have a to the power of the logarithm with base a of b, this is simply b. Now why this works is of course because this exponent here, this logarithm base a of b, is exactly the exponent that we need to lift a to in order to get b. And if this is already in the exponent, well, then of course we just get b. That's basically the definition of the logarithm. And because we have this combination of 3 to the power of logarithm base 3, we can simply use whatever is inside the logarithm. So we have 5x minus 2, which is still equal to 3 to the power of 2. And again, this is where we used this property or definition of the logarithm. And now we see that we have reduced our logarithmic equation to a simple algebraic equation, which we know immediately how to solve. So we can rearrange this. We have 5x is equal to 9, because 3 to the power of 2 is 9, plus 2, which is of course equal to 11. And therefore we immediately find that x has to be equal to 11 divided by 5. And this is our result, which again we can check by plugging it in back into our original equation. We see that we get the logarithm of base 3 of 5 times 11 divided by 5, which is our solution x minus 2, is equal to the logarithm base 3 of 9. And here we of course know that the logarithm base 3 of 9 simply asks to what power do we have to raise 3 in order to get 9? Well, this is of course simply 2, since 3 to the power of 2 is equal to 9. And we see that indeed this is what our original equation said. So our solution is indeed the correct one. So let's now do another exercise where we have to use this trick in order to get some feeling with it. In exercise 4 we have the following equation. The ln of x to the power of 2 plus 3 has to be equal to 10. And here we have again a new notation, which is the ln of x, which basically is the logarithm with base number e of x. And e is of course the famous Euler's number. And because the logarithm with a base e occurs so much both in mathematics and physics, we simply give it a new name, the natural logarithm, and we write it as ln. But this is of course just convention, but important convention. Again, we see here that one term indeed has a logarithm, but another term doesn't have a logarithm. So we cannot use the same method that we did at the start of this video. However, we can use the trick that we had before, simply exponentiating both terms of our equation by the base number of our logarithm. In this case, the base number is e, because we have a natural logarithm. So this becomes, of course, the following. We have e to the power of ln of x squared plus 3 on the left-hand side and e to the power of 10 on the right-hand side. Now again, what was valid for all logarithms is also valid for natural logarithms, namely that e to the power of ln of x is simply x, because the ln of x simply asks what power do we need to lift e to in order to find x, and therefore e to the power of ln of x is of course simply x. And because on the left-hand side we have this combination of e to the power of ln, this will simply become whatever is inside the ln. So we can write this as follows. We have x squared plus 3 is equal to e to the power of 10. Now this of course is simply just an algebraic equation which we can readily solve as x squared is equal to e to the power of 10 minus 3. And by simply taking the square root of both sides of the equality sign, we get the following, that x is equal to the square root of e to the power of 10 minus 3. And this is our solution for our logarithmic equation where we had a natural logarithm. And again, if we simply fill this in our original equation, we can see whether we made any mistake. So we get the natural logarithm of x squared, which is simply this thing squared, so the square root drops, of e to the power of 10 minus 3, and we don't forget this plus 3, which is of course equal to, if these two 3's cancel, we have the natural logarithm of e to the power of 10, and here we can of course see that this is simply 10, our right-hand side, so we know that we didn't make any mistakes. So now that we've used these tricks, let's go to the next exercises, where we will be using some more properties of the logarithm. Our fifth exercise will be the following equation. We have the logarithm of base 2 of x plus 5 minus the logarithm of base 2 of x plus 1, and this has to be equal to the number 5. Now the first thing that we note is that we indeed have two terms with a logarithm with the same base, but we also have a term that does not contain a logarithm, so we cannot use the trick that we used in the first two exercises. We also cannot use the second trick by simply exponentiating both sides of the equality sign, because here we have this annoying minus sign. We have two terms on the left-hand side. So what do we actually do in this case? Well, we remind ourselves of two important properties of logarithms. If we have the logarithm of any base of a number a, and we add to this the logarithm of the same base of another number b, then we simply have the logarithm of the same base again of a multiplied with b. And the same holds if we subtract these two logarithms. If we have the logarithm of a minus the logarithm of b, then we get the logarithm of now a divided by b. And note here that it's very important that all of these logarithms have the same base and that there is no number in front of these logarithms, so they don't have any coefficient. Now we see that we can use this property in this exercise right here, because we have the logarithm with a base of 2 minus another logarithm with the same base of 2. So we can use this property right here, simply the subtraction of two logarithms. So we get the logarithm of base 2 of the following. We have the first logarithm, so x plus 5, and we divide it by the second number, which in this case is x plus 1. And on the right hand side, we simply leave our number 5. And in this case, we indeed have reduced our logarithmic equation to where on one hand side, we have just one logarithm of base 2, and on the right hand side, we have a simple number. And this is, of course, the same situation that we had in exercise 3 and exercise 4, where we saw how to solve such a scenario. Simply exponentiate both sides on the equality sign with a base number that is the base of the logarithm. So let's do that right now. This means that our equation can be rewritten as 2 to the power of the logarithm with base 2 of x plus 5 divided by x plus 1. And on the right hand side, we have 2 to the power of 5. And we can already write that 2 to the power of 5 is simply 32. And again, we have this combination of 2 to the power of the logarithm with base 2. And this combination will always make it so that we only are left with the thing that is inside of this logarithm. So this equation becomes the following. We have x plus 5 divided by x plus 1, which is equal to 32. And in this way, we have reduced our initial logarithmic equation all the way to an algebraic equation, which we can now very easily solve. We find, of course, by bringing this denominator to the other side of the equality sign, that x plus 5 has to be equal to 32x plus 32. Bringing all terms with an x to the left-hand side of the equality sign, so bringing this term to the other side, we find that x minus 32x is equal to 32 minus 5, bringing this plus 5 to the other side. This can be very easily calculated to be minus 31x is equal to 27, or simply finding our solution that x is equal to 27 divided by minus 31. And there we go, we already have our solution right here. Now as a check, you can of course plug this in our original equation, but I will leave that to you as another exercise. And let's now go to a following exercise. In the sixth exercise, we have that the natural logarithm of x, so the logarithm with base e of x, has to be equal to 1 plus the natural logarithm of x minus 1. So how do we solve this one? Well, first, we notice that we have two terms with a logarithm with the same base. However, we have this 1 which is not a logarithm. So we cannot simply use whatever is inside the logarithm as we did in exercise 1 and 2. We can also at this point not yet exponentiate both sides of the equality sign because we have this plus of two terms right here, which prevents us from doing so. So what we do in this case, and in any case really, is to bring all of the logarithm stuff to one side of the equality sign. So we have the logarithm of x minus the logarithm of x minus 1, which is equal to simply 1. And now we can use the property of logarithms that we had before, because we have the subtraction of two logarithms with the same base here. So this simply becomes the following: the natural logarithm of x divided by x minus 1. And this has to be equal to 1. And at this point, we can use this exponentiating trick, because we only have one logarithm on the left-hand side and a number on the right-hand side. Therefore, we're going to exponentiate both sides, and we're going to exponentiate it with a base number of e, because again, the natural logarithm is simply the logarithm with base e. So we have e to the power of the logarithm of x divided by x minus 1, and this has to be equal to e to the power of 1, which is of course simply e. Again, because we have this e to the power of ln of something, this is simply equal to whatever is inside of the logarithm. So we can write x divided by x minus 1 is simply equal to e. And again, we have reduced our logarithmic equation to an algebraic equation, which we can now readily solve. We have x on the left-hand side is e multiplied by x minus 1 on the right-hand side, which is equal to e times x minus e. Bringing this e times x to the left-hand side, we have x minus e times x, which is simply equal to minus e. And rewriting this even further, we have x times 1 minus e, which is equal to minus e. And this brings us to our solution that x has to be equal to minus e divided by 1 minus e. Or bringing this minus sign in the numerator to the denominator, we simply have e divided by e minus 1. And this, well, looks much nicer as a solution. And there we have it, already a solution to our initial logarithmic equation. And as always, we can fill this in our original equation, and we'll see that this equality sign is indeed true, and it's a good exercise for you to get some more algebraic practice. And let's now bring all of this together in our 7th and final exercise, which will take a bit more calculation, but the same tricks apply. We have our equation that the logarithm with base 5 of x plus 2 minus the logarithm of base 5 of simply x has to be equal to the logarithm of base 5 of 2x minus 1 minus the logarithm of base 5 of 3x minus 12. And the first thing that we see here is that each term has indeed a logarithm with the same base. However, there's still this annoying minus sign, so we have 4 terms. And what we would like is just to have one logarithm on one hand side and one logarithm on the other side of the equality sign. So first we use the property of adding and subtracting logarithms. Since they all have the same base, we can simply do this. So we get the logarithm with base 5 of x plus 2 divided by x on the left hand side, and on the right hand side we simply have the logarithm of base 5 of 2x minus 1 divided by 3x minus 12. And at this point we don't even need to use the exponentiation trick that we did before, because we can simply use the procedure that we did in exercise 1 and 2, because on both hand sides of the equality sign we simply have one term which is a logarithm with the same base. And this means that we can simply use whatever is inside of the logarithm and put an equality sign in between them. So in this case we simply get x plus 2 divided by x is equal to 2x minus 1 divided by 3x minus 12. And we have reduced yet again our original logarithmic equation to a simple algebraic equation. And this is the one that we're going to solve right now in order to get our solution. This means that we get x plus 2 multiplied by 3x minus 12 has to be equal to 2x minus 1 times x. Computing these brackets, we get on the left hand side 3x squared minus 12x plus 6x minus 24 is equal to 2x squared minus x. Bringing everything to the left-hand side of the equality sign, we have 3x squared minus 2x squared, which is this term right here, minus 12x plus 6x plus x, which is this term right here, minus 24 is equal to 0. And now taking all of the terms with equal powers of x together, we have x squared minus 5x minus 24 is equal to 0. And this is now simply a second order equation, which of course we know how to solve. We have that x plus or minus, because we have two solutions, is equal to minus b, which is in this case minus negative 5, so plus 5, plus or minus the square root of b squared, which is 25, minus 4 times a times c, which in this case is minus 4 times negative 24. We divide this by 2 times a, and a is in this case simply 1, so we get 2. And now computing what is inside of the square root, we get 5 plus minus the square root of 25 plus 96 divided by 2. Now we know of course that 25 plus 96 is 121, and the square root of 121 is simply equal to 11. So we get 5 plus minus 11 divided by 2. And this will give us two solutions. We have 5 plus 11, which is 16, divided by 2, which is simply 8. And we have another solution where we have 5 minus 11, which is equal to minus 6. And we have to divide by 2 in order to get the other solution, minus 3. So at this point, we have two solutions, 8 and minus 3. But what is now the right solution? For this, let's go back to our original logarithmic equation. We see that we have the logarithm of x plus 2, x here, 2x minus 1, and 3x minus 12. Now what is important here to realize is that the logarithm of any base of a number that is smaller than 0 is ill-defined, so this cannot happen. Therefore, if we have a solution, and again our solutions were x is equal to minus 3 or x is equal to 8, if one of these solutions makes it so that we have a negative number inside of the logarithm, then we can already cancel that solution. And we see, of course, in the first term already that we have x plus 2. Now, if x is minus 3, then we would get minus 3 plus 2, which is, of course, minus 1. And we would get the logarithm of minus 1. And that is, of course, not allowed. Therefore, we conclude that the only solution that we have is x is equal to 8. So if we fill in x is equal to 8, we will indeed see that this equality sign holds. And this shows that even though you can simply go through the calculations, in the end you still need to think about what your result actually is and if it even makes sense. For instance, if you concluded here that we have two solutions, then that would be a wrong conclusion, since one solution can be dropped and we only have one unique solution. And this brings us to the end of this video, and I hope that you're now more familiar with solving logarithmic equations. If you appreciate the effort that goes into making these videos, give them a thumbs up. You can also subscribe to get notified by future releases. And again, if you have any questions, leave them in the comment section below or join our Discord server. And with that, I thank you for watching, and I will see you in the next one. Bye.